The universe is slowly turning off the lights. Galaxies, those vast islands of stars, are not permanent. They are entering a state of cosmic silence, a slow fade into darkness that will define the future of everything. This is the story of galactic death. By the end, you will understand not only how galaxies die, but how this grand fate redefines our own place in the cosmos. We will uncover what forces strangle star formation and what happens when a galaxy's central black hole falls quiet. What does it truly mean to watch a city of stars go dark? This vibrant golden age cannot last forever. To grasp the quiet end awaiting these stellar metropolises, we need to see them not as static pictures, but as living entities with their own life story. Every galaxy you see in a telescope image has a birth, a period of thriving maturity, and an inevitable, slow decline. It begins in the deepest emptiness of the early universe, where vast, formless clouds of primordial hydrogen and helium, the universe's original ingredients, slowly begin to gather. Gravity is the sculptor here, patiently pulling these tenuous gases together over hundreds of millions of years. As these clouds condense and collapse, the first pockets ignite, sparking the birth of the very first stars. These pioneer stars are massive, brilliant, and short-lived, but their explosive deaths seed the cloud with heavier elements, the cosmic dust and ash that will become the building blocks for future planets and, ultimately, life. This is the galaxy's infancy, a chaotic and fiercely creative nursery. From this turbulent beginning emerges a more structured form. For a galaxy like our own Milky Way, this is the long, stable era of maturity, a period lasting billions of years. Think of a great city in its prime. Spiral arms like bustling interstellar highways are lined with glowing stellar nurseries, the pink and red nebulae where new stars are constantly being born. Brilliant blue, hot young stars light up the neighborhoods, while older, yellow stars like our Sun provide steady light for eons. Supernova, the spectacular final acts of massive stars, periodically enrich the galactic environment with new heavy elements. This is the galaxy at its most productive, a dynamic ecosystem where gas is constantly being recycled from old stars into new ones. It is a cycle of cosmic renewal that feels perpetual. But just as a thriving city can face resource depletion or changing conditions, a galaxy's vibrant star-forming era is sustained by a finite fuel supply, cold, dense gas. The central mystery of galactic death is not a sudden explosion, but the slow, relentless strangling of this creative engine. What internal and external forces conspire to shut down the star-forming factories, and what remains when the lights finally begin to wink out, one by one? The transition from a living galaxy to a cosmic fossil is the true meaning of galactic death. It is not a violent end, but a profound and permanent change of state. Imagine a great forest that has stopped growing new trees. The oldest giants still stand, their leaves turning from vibrant green to autumnal gold, and finally to a deep, uniform crimson, but no saplings rise to take their place. The ecosystem has entered a lasting stillness. This is precisely what astronomers witness in the so-called dead galaxies scattered throughout the universe. Their defining characteristic is the complete cessation of star birth. The vibrant pink nebulae, the stellar nurseries that once dotted spiral arms like clouds of cosmic fireflies, have vanished. The fuel for new stars, the cold, dense clouds of interstellar gas, has been exhausted, heated beyond use, or stripped away entirely. What remains is a population of aging stars, left to shine with the light they were born with, slowly cooling and reddening over billions of years. This is why these galaxies often appear as smooth, reddish blobs in our telescopes. their distinct spiral structures blurred into a featureless haze of ancient suns. They have become celestial archives, preserving a snapshot of a final generation of stars, with no new chapters being written. This slow fade from blue and white to a solemn red is the galaxy's final color, a visual signature of its quiet passing into cosmic silence. But what force could possibly choke off a galaxy's entire future? The answer lies in a cosmic process astronomers call quenching. This is the slow, steady suffocation of a galaxy's star-forming engine, and it can happen in several devastating ways. The most straightforward culprit is simple exhaustion. A galaxy is born with a vast reservoir of cold, dense gas, but it is not an infinite supply. Over billions of years, as generation after generation of stars form, this fuel is gradually locked away. Each new star is a prison for that gas, holding it for millions or billions of years. When massive stars die in supernova, they do return some enriched material to the galactic environment, but it is often blown so far and heated so intensely that it cannot easily cool down and collapse into new stars again. It is like a campfire slowly burning through its last logs, the flames growing weaker as the available fuel turns to ash and embers that cannot be rekindled. Yet, exhaustion is not the only path to silence. Often, the gas is not just used up but actively stolen or destroyed. Inside a thriving galaxy, the very processes that create stars can also seal their fate. Supernova explosions, while brilliant, send colossal shockwaves through surrounding gas clouds, heating them to millions of degrees and blowing them clear out of the star-forming regions. This is stellar feedback, a self-regulating mechanism that can eventually turn against the galaxy itself, preventing gas from ever cooling back down to the dense, cold state needed for new birth. An even more powerful internal force resides at the very heart of most large galaxies, the supermassive black hole. When such a black hole actively feeds on surrounding matter, it becomes an active galactic nucleus, unleashing unimaginable energy in the form of intense radiation and jets of particles that can travel for thousands of light years. These jets act like cosmic blowtorches, heating the galaxy's remaining gas reservoir to such extremes that it simply cannot collapse. The galaxy's own central engine, in its most violent state, can sterilize its entire home, ensuring no new stars will ever form again. But the threats are not only internal. A galaxy's environment can be just as hostile. In the crowded confines of a galaxy cluster, a spiral galaxy moving at high speed through the thin, superheated plasma that fills the space between galaxies can experience a phenomenon called ram pressure stripping. Imagine holding a delicate dandelion seed head out of a car window at high speed. The rushing wind violently strips away the delicate filaments. In a similar way, the intracluster medium acts as a relentless headwind, violently stripping a galaxy of its cold gas, ripping the very fuel for future stars right out of its grasp. Finally, there are gravitational interactions and mergers. When two galaxies collide, it can initially trigger a spectacular firestorm of new star formation as their gas clouds are violently compressed. This seems like a rebirth, yet paradoxically, such a dramatic event can also be the beginning of the end. The tremendous gravitational turmoil can funnel vast amounts of gas directly into the central black holes, igniting those devastating feedback jets that heat or expel the remaining gas. Or the merger can completely reshape the galaxy, transforming a gas-rich spiral into a smooth, gas-poor elliptical galaxy, effectively ending its star-forming days. So quenching is not one single event but a menu of grim possibilities. A galaxy might slowly starve, be burned from within by its own heart, be robbed by its environment, or be reshaped by a catastrophic merger. Each pathway leaves a different fingerprint on the galaxy's final state, a cosmic clue for astronomers to decipher as they trace the slow transformation of vibrant cities of light into silent, red monuments of the past. At the very heart of this slow transformation lies a profound paradox. The same cosmic furnaces that once helped forge a galaxy can become the instrument of its silencing. This brings us to the role of the supermassive black hole, an entity so extreme it defies everyday understanding, yet it acts as the galaxy's ultimate regulator. Think of it not as a mindless vacuum, but as the galaxy's hidden heartbeat. When this colossal heart beats strongly, fed by rivers of infalling gas and dust, it awakens as an active galactic nucleus. In its most spectacular form, this can be a quasar, outshining the combined light of every star in its host galaxy. Or it can blast out focused jets of energy and particles that stretch for thousands of light years across the cosmos. This isn't just a light show, it's a fundamental force shaping the galaxy's destiny. The energy pouring from the active black hole floods the surrounding space, acting like a colossal cosmic heater. It superheats the vast reservoirs of gas that would otherwise cool, condense, and birth new stars. In this way, the black hole acts as a galactic thermostat, preventing the galaxy from forming stars too quickly and burning through its fuel in a brief, fiery burst. It enforces a kind of balance, a measured pace of stellar creation that can sustain a galaxy for billions of years. But this balance is a delicate one, entirely dependent on a steady fuel supply. As the galaxy ages and its usable gas is depleted, starved, or stripped away, the rivers feeding the central black hole begin to slow to a trickle and then stop altogether. The brilliant quasar fades, the powerful jets sputter and fall silent. The galactic heartbeat grows faint and then ceases. This quieting of the central engine marks a critical transition. With a regulating heat from the black hole gone, you might think star formation could reignite. Yet, by this point, it's often too late. The remaining gas has either been permanently heated, blown away, or locked inside aging stars. The thermostat is broken and the furnace has run out of fuel. The galaxy is left in a state of profound equilibrium, a quietude where nothing new is born and nothing is violently destroyed. The supermassive black hole still resides at the center, but it is a dormant giant, a sleeping monarch in a palace grown cold and still. This intricate dance between creation and regulation, between a vibrant heartbeat and final silence, shows us a stunning truth. The ultimate fate of a vast island of stars, home to hundreds of billions of suns, is intimately tied to the behavior of its most extreme and invisible inhabitant. The story of a galaxy's life and long, slow death is written not just in its stars, but in the dark heart at its core. The vibrant life and quiet death of every star is a story written in light and gravity. To truly grasp a galaxy's slow fade, we must first understand the fate of its individual citizens, the stars themselves. Each one begins its journey not in isolation, but within a bustling stellar nursery, a dense, cold cloud of gas and dust nestled inside a galaxy's spiral arm. Under the relentless pull of gravity, a small fragment of this cloud collapses inward, spinning and heating until the core becomes so incredibly hot and dense that it triggers a miraculous process, nuclear fusion. In that instant, hydrogen atoms are fused into helium, releasing a torrent of energy that pushes outward, balancing the crushing force of gravity. A star is born, and it will shine for an unimaginably long time, its entire destiny dictated by a single, simple property, its mass. A star's mass is its fortune and its fate. The smallest stars, known as red dwarfs, are incredibly frugal with their nuclear fuel. They burn their hydrogen slowly and steadily and can shine for trillions of years, far longer than the current age of the universe. They are the ultimate cosmic survivors, destined to outlive every other type of star. In contrast, massive stars live lives of extravagant brilliance and shocking brevity. They burn through their core hydrogen in just a few million years, a cosmic blink of an eye. Their deaths are not quiet. When such a giant star finally exhausts its fuel, its core collapses catastrophically in a supernova explosion, an event so violent it can briefly outshine its entire host galaxy. This spectacular end is not a waste, it is essential. The titanic forces of the supernova forge elements heavier than iron like gold, silver, and uranium and blast them across interstellar space. This stellar ash becomes the raw material for new stars, planets, and eventually life. The star dies, but its legacy is woven into the fabric of the galaxy. What remains after this brilliant finale depends entirely on the star's initial mass. For a star like our Sun, the end is a more gentle transformation. After swelling into a red giant, it will shed its outer layers into space, creating a beautiful, glowing planetary nebula. The hot, dense core that is left behind will cool forever as a white dwarf, an Earth-sized ember of degenerate matter, slowly fading into darkness over tens of billions of years. For the more massive stars that go supernova, the remnant is even more extreme. The collapse can leave behind a city-sized sphere of unimaginably dense material called a neutron star, where a teaspoon of matter would weigh as much as a mountain. Or if the core is massive enough, the collapse does not stop at all, resulting in the birth of a stellar mass black hole, a point of infinite density shrouded by an event horizon from which not even light can escape. This cycle from nebular birth to silent remnant is the fundamental pulse of a galaxy. For billions of years, this cycle drives the galaxy's evolution, recycling gas, creating heavy elements, and lighting the cosmic dark. But in a galaxy that is dying, this cycle is broken. The stellar nurseries empty, and no new stars are born to replace the old. One by one, the massive stars blaze out in their final supernova. The Sun-like stars exhaust their fuel and shrink into faint white dwarfs. The red dwarfs continue their slow, steady glow, but they are the dim candles of the cosmos. Over eons, the collective light of the galaxy shifts and dims, not from a single catastrophe, but from the accumulated silence of countless individual stellar lives reaching their inevitable, quiet ends. The galaxy's grand narrative is simply the sum of all these tiny, brilliant stories, and when the last chapter is written for the last star, the transformation into cosmic silence is complete. This cosmic transition from blue to red is not a subtle artistic shift. It is a fundamental change in a galaxy's state of being, and astronomers can actually map it. The tool they use is deceptively simple, a kind of cosmic family portrait known as the color magnitude diagram. By plotting thousands of galaxies based on their overall brightness and their color, a stunning pattern emerges. The diagram reveals a clear fork in the road. On one side, you have a broad, scattered cloud of galaxies that are blue and bright. These are the star-forming powerhouses, alive with the energetic light of hot, young, massive stars. Their spiral arms are bustling with activity. On the other side, you see a tight, narrow band of galaxies that are uniformly red and generally fainter. This is known as the red sequence. These are the quiescent galaxies, the ones where star formation has ceased. Their light comes almost entirely from older, cooler, redder stars, all aging in unison. The stark division between these two groups is what astronomers call a bimodal distribution. It suggests that galaxies don't just slowly drift from blue to red over time. Instead, something profound happens. A galaxy can live for billions of years in the blue cloud, actively creating new generations of stars. Then, relatively quickly in cosmic terms, it undergoes a transformation. The star-forming engine is shut down. Once that happens, the galaxy seems to rapidly cross a gap and settle onto the red sequence, where it will remain for the rest of cosmic time. This is the observational fingerprint of galactic death. The red sequence is a graveyard of sorts, but it is a graveyard filled with silent, glowing monuments. The mystery embedded in this diagram is intense. What is the trigger that forces a galaxy to make that rapid, one-way journey? And why, once a galaxy joins the red sequence, does it seem impossible for it to return to the vibrant blue cloud? It's as if a biological organism reaches a certain point of maturity and then undergoes a permanent change with no path back to youth. Studying the galaxies strung along this diagram is like reading a cosmic history book. We can see the vibrant, star-forming galaxies at the peak of their lives. We can identify galaxies that are in the process of quenching, perhaps showing signs of both blue and red light as their star formation sputters out. And we can examine the pristine, red and dead galaxies that have been silent for eons. This allows astronomers to trace the evolutionary paths to find the point of no return. The evidence suggests that the transition is often linked to a catastrophic event, like a major merger that exhausts or expels the gas, or the violent feedback from a central black hole that heats the galactic fuel supply to a permanent simmer. After such an event, the galaxy's remaining stellar population is left to age in lockstep, without new, blue stars being born to interrupt the reddening glow of the old ones. The entire galaxy shifts color in unison. It joins the red sequence and becomes a closed system, its story essentially complete. This cosmic diagram tells us that the death of a galaxy is not a random accident, but a distinct phase in a predictable life cycle, a final chapter written in the fading light of countless ancient suns. The final color shift into red is only the beginning of the silence. To truly comprehend the scale of galactic death, we must stretch our minds across a timeline of almost unimaginable length. This is not a story of days or years, but of cosmic epochs where a single chapter can last longer than the current age of our planet. For a massive galaxy like those we see in the red sequence today, the quenching process, the slow strangling of its star-forming engine, likely began around 10 billion years ago. That is a staggering thought. When the universe itself was only about a third of its current age, these galaxies were already beginning their long, slow fade from vibrant blue to solemn red. The decline in star formation is not a cliff, but a gentle, relentless slope spanning several billion years. Generation by generation, the stellar nurseries empty, the brilliant blue giants vanish, and the rate of new births dwindles to a whisper and then to nothing. What follows is an even more profound stillness. Once the last new star is born, the galaxy enters a phase defined not by creation, but by patience. The existing population of stars is left to live out their natural lives on schedules dictated by their mass. The sun, like stars, will shine for billions of years before shedding their outer layers and cooling as white dwarfs. But the true long-distance champions are the smallest stars, the red dwarfs. These frugal, dim stars burn their hydrogen fuel so slowly that they can shine for trillions of years. They will become the final sentinels of light in these dying galaxies, glowing with a faint, ruddy hue long after every other star has faded. Their persistent light means a so-called dead galaxy is not truly dark for an almost incomprehensible span of time. It simply becomes a museum of aging suns, a cosmic clock ticking down at a pace that defies human intuition. This leads us to the ultimate fate of not just one galaxy, but of the entire cosmos. Astronomers project forward to an era they call the Degenerate era, which will begin perhaps 100 trillion years from now. By this point, the last red dwarf will have finally exhausted its fuel. The universe will no longer be lit by the steady fusion of new stars. Instead, it will be a realm of relics and remnants. The sky will be dotted with the cooling embers of white dwarfs and the incredibly dense spheres of neutron stars, all slowly radiating away their last traces of heat into an ever-expanding, ever-colder void. Supermassive black holes will still loom in the centers of the ancient galactic husks, but they will be dark and silent, growing only imperceptibly by capturing the rare bit of stray matter that drifts too close. This is the universe's final configuration, a silent, dark, and profoundly simple state. Contemplating this timeline does more than just inform us, it fundamentally reshapes our perspective. Our entire recorded history, the rise and fall of civilizations, the lifespan of our species, even the age of our planet, are less than a blink in this grand narrative. The death of a galaxy is a process so slow and vast that from our fleeting vantage point, it appears as a permanent state. We simply see a red, quiet galaxy and call it dead, not realizing we are catching it in the middle of an eons-long final act. This cosmic perspective is both humbling and strangely liberating. It reminds us that the universe operates on a canvas of time and space that transcends our everyday experience, writing its story in chapters that last for epochs. To understand galactic death is to begin to read that story, to see the universe not as a static backdrop, but as a dynamic, aging entity with a past, a present, and a quiet, distant future written in the fading light of countless stars. While a galaxy's internal heart can seal its fate, its cosmic neighborhood often writes the final sentence. The environment a galaxy lives in is not a passive backdrop. It is an active, often brutal force that can accelerate its journey into silence. This is starkly evident when we compare two cosmic settings, the isolated, peaceful field and the dense, crowded city of the galaxy cluster. A lone spiral galaxy drifting in the relative emptiness of intergalactic space is like a self-sufficient island. It holds onto its precious reservoirs of cold gas, cycling it through generations of stars at its own pace, largely undisturbed by external threats. Its destiny is primarily shaped by its own internal processes, the slow exhaustion of fuel or the feedback from its central black hole. But place that same spiral galaxy into the heart of a massive cluster, and its story changes dramatically. Galaxy clusters are the metropolises of the cosmos, containing hundreds or even thousands of galaxies bound together by immense gravity, all moving at tremendous speeds through a thin, superheated plasma known as the intracluster medium. This environment is extraordinarily hostile to star formation. The primary killer here is a process with a vividly descriptive name, ram pressure stripping. Imagine our spiral galaxy with its extended disk of gas and dust plunging at millions of miles per hour through this seething, thin broth of million-degree plasma. The sensation is like sticking your hand out of a car window at high speed, feeling the rush of wind forcing your fingers back. For the galaxy, this intergalactic wind is far more violent. It acts like a cosmic pressure washer, relentlessly scouring the galaxy's disk. The delicate, cold clouds of gas that are the raw material for new stars offer little resistance. They are simply torn away, stripped from the galaxy's gravitational grasp, and lost to the vast, hot emptiness between the cluster's members. The galaxy is robbed of its future. Without its gas, star formation grinds to a halt almost immediately. What remains is a galaxy that may still look like a spiral from the outside, its skeletal structure of old stars intact, but it has been gutted of its creative potential. It becomes what astronomers call a red and dead spiral, a ghost of its former self, rapidly joining the red sequence. This environmental quenching is often faster and more ruthless than the slow internal strangulation of a field galaxy. It explains a clear pattern we observe. Dense galaxy clusters are dominated by these red, quiescent galaxies, while the blue, star-forming spirals are found more frequently in the isolated field. This raises a profound mystery for modern astrophysics, a kind of nature versus nurture debate on a cosmic scale. To what extent is a galaxy's fate predetermined by its intrinsic properties, like its mass or the size of its central black hole, and how much is dictated by the sheer luck of its cosmic address, the environment it was born into or fell into later in life? Quantifying this balance is one of the key challenges in understanding cosmic evolution. Does a galaxy's own heart fail first, or is it murdered by its neighborhood? The evidence suggests both paths are possible, and sometimes they work in concert. A galaxy entering a cluster may have its gas stripped, silencing it. But that same traumatic entry can also funnel gas toward its central black hole, triggering a final, violent outburst of feedback that seals the deal. The cluster, therefore, is not just a collection of galaxies. It is a cosmic ecosystem with its own rules, a place where the slow transformation into silence is often hastened by the relentless physics of a crowded and violent universe. A perfect specimen of this cosmic silence hangs in the constellation Virgo. Messier 87 is not a delicate spiral, but a colossal, smooth ellipse of ancient light, a titan reigning at the gravitational center of the Virgo cluster. Its very form tells a story of a violent and consumptive past. Unlike our own Milky Way with its star-forming arms, M87 presents a featureless golden haze, the combined glow of countless aging suns. This uniformity is the hallmark of a galaxy whose star-forming days ended billions of years ago. Its remaining stellar population is old, having aged together in isolation, with no newborn blue stars to disrupt the serene, reddish-yellow complexion. This giant did not fade quietly from within. It achieved its silent majesty through a more dramatic and imperial path, growing to its enormous size by consuming its neighbors. The evidence for this galactic cannibalism is written in the faint archaeology surrounding it. M87 is famously surrounded by a staggering halo of over 10,000 globular clusters, dense spherical swarms of ancient stars. This is an order of magnitude more than the Milky Way possesses, and astronomers interpret this excess as the accumulated trophies of devoured dwarf galaxies. Each cluster is like a distinct stellar family, a preserved relic from a smaller system that was long ago torn apart and absorbed. Even more telling are the faint, ghostly streams of stars that arc through its outer reaches, the final, dissolving signatures of galaxies caught in M87's immense gravitational pull and stretched into cosmic taffy over eons. These streams are the archaeological strata of this giant, layered records of a history written in collisions. The galaxy's own structure supports this narrative. The chaotic mergers that built it would have violently scrambled any orderly spiral disk, funneling gas inward to trigger ferocious bursts of star formation and feed the central black hole, ultimately leaving behind the smooth, puffed-up elliptical we see today. And at the very heart of this silent giant lies the most famous resident of all, the supermassive black hole whose shadow was first captured by humanity. This black hole, with a mass billions of times that of our Sun, is now relatively quiet, a dormant monarch, but its past activity is believed to be the key final actor in M87's story. During the era of violent mergers, vast amounts of gas would have flooded into the galactic center, igniting the black hole as a powerful, active galactic nucleus. The resulting jets and radiation likely provided the final, decisive feedback that heated or expelled the last of the galaxy's remaining gas, permanently shutting down the star-forming factories and ensuring the uniform aging of its stellar population. Today, M87 stands as a majestic endpoint, a fossil of a bygone era of cosmic violence, now resting in a state of profound and beautiful equilibrium. It shows us that the most massive galaxies in the universe often reach their silent state not through gentle exhaustion, but through a dramatic series of mergers, growing to immense size by assimilating others, with their central black holes acting as the final guarantors of permanent quiet. The grand, silent fate of galaxies like Messier 87 is not just a distant spectacle. It is the future written for our own home. The Milky Way, with its shimmering spiral arms and brilliant stellar nurseries, is currently a vibrant member of the blue cloud, a galaxy in its prime. Yet, like all things in this evolving universe, its current state is temporary. Its destiny is already set in motion by the relentless pull of gravity across the vast, dark gulf of intergalactic space. Our nearest large galactic neighbor, the Andromeda Galaxy, is on a collision course with us, moving closer at a staggering speed of about 110 kilometers per second. In approximately 4.5 billion years, the two great spirals will meet. This will not be a sudden, catastrophic crash, but a slow, majestic, and chaotic dance lasting hundreds of millions of years. As the galaxies first swing past each other, their immense gravitational fields will act like tidal forces, violently distorting their beautiful spiral structures. Long streamers of stars and gas will be pulled out into space, creating breathtaking, if terrifying, celestial arcs across the future night sky. This gravitational turmoil will compress vast reservoirs of gas within both galaxies, triggering an immense, fireworks-like burst of new star formation. For a time, the merged galaxy will blaze with the light of billions of newborn stars, a final, brilliant crescendo of cosmic creation. But this fertile firestorm contains the seeds of its own end. Such a violent merger is incredibly efficient at funneling gas directly into the supermassive black holes at the hearts of both galaxies. This will likely ignite them as brilliant quasars or unleash powerful jets, flooding the system with energy that heats and expels the remaining star-forming fuel. Furthermore, the chaotic gravitational interactions can simply throw much of the gas out of the new galaxy entirely, scattering it into the intergalactic void. After multiple close passes, the two galaxies will finally coalesce, their stars merging into a single, new entity. Astronomers have already given this future giant a name, Milkomeda. It will not be a spiral. The violent merger will have completely scrambled any orderly disk, leaving behind a smooth, featureless, elliptical galaxy. With its gas exhausted, expelled, or heated into permanence by the awakened black holes, star formation will grind to a halt. Milkomeda will then begin its long, slow transition onto the red sequence. Its population of stars, a mix of survivors from both the Milky Way and Andromeda along with the final generation born during the merger, will age together. Over the eons that follow, their collective light will shift from blue and white to gold, and finally to a deep, uniform red. Our solar system will likely be flung into a much more distant orbit within this new elliptical giant. But Earth itself will have long since been rendered uninhabitable by the swelling of our own sun. This personalized timeline makes the abstract concept of galactic death profoundly tangible. It shows us that the cosmic cycle of transformation and silence is not something that happens only to others out in the depths of space. It is the inevitable future of our own stellar city. The Milky Way story has a final chapter, and it is one of brilliant, chaotic rebirth followed by an eternal, quiet fading. This knowledge reframes our place in the cosmos. We are living in the galaxy's golden age, a fleeting period of creativity and light that will one day be seen as the vibrant youth of a future silent giant. The disappearance of a galaxy's star-forming fuel is the central crime scene of galactic death. We know the cold, dense gas must vanish, but its exact fate remains one of the most compelling mysteries in modern astrophysics. Where does it all go? It doesn't simply evaporate. Matter is conserved in the universe. Instead, the gas undergoes a dramatic transformation, changing its state or location so completely that it can no longer participate in the beautiful, creative act of star birth. Solving this requires us to think like cosmic detectives, tracking the flow of matter on the grandest scales through what astronomers call the Baryon cycle. This is the story of how a galaxy's lifeblood is moved, heated, and sometimes stolen away. One primary suspect is extreme heating. When gas is superheated to millions of degrees, it enters a state where individual atoms move so fast and are so spread out that gravity cannot pull them together to form the dense cores of new stars. This heating can come from multiple sources. The collective fury of supernova explosions from massive stars can flood a galaxy's interior with energy, creating a hot, high-pressure environment that prevents gas from cooling. Even more potent is the feedback from an active supermassive black hole, whose radiation and jets can act like a cosmic blowtorch, boiling the galactic reservoir. In this scenario, the gas is still technically present, but it's in a form as useless for star formation as steam is for putting out a fire. It's there, but it cannot condense. Alternatively, the gas might not just be heated but violently expelled. Galactic winds driven by those same supernova or black hole jets can achieve escape velocity, blowing the gas clear out of the galaxy's gravitational grip and into the vast intergalactic medium. This is a permanent loss, like a tree losing its seeds to a hurricane, scattering them far beyond where they could ever take root. We see evidence of these winds as faint, extended halos of hot gas around galaxies, detected not in visible light but in the high-energy glow of X-rays. The galaxy is literally bleeding its future into space. Then there is the ultimate consumer, the central black hole itself. While a black hole is famously picky and only consumes matter that crosses its event horizon, the process of feeding is messy. Vast amounts of gas can be funneled toward the galactic center, swirled into a glowing accretion disk, and a portion of it is ultimately captured. This consumption is relatively small in terms of total mass, but the energy released in the process is what makes the black hole such an effective regulator, often heating or expelling the far larger remaining gas reservoir. So the black hole might eat a little, but its real impact is in how it spoils the rest of the pantry. The environment offers another clear-cut answer, especially in the crowded metropolis of a galaxy cluster. Here, the process of ram pressure stripping acts like a cosmic car wash, with the thin, superheated plasma between galaxies scouring a spiral clean as it moves at high speed. The cold gas is ripped directly from the galaxy's disk, leaving behind a gas-poor skeleton of stars that rapidly reddens and fades. This stripped gas doesn't vanish. It joins the cluster's own hot atmosphere, contributing to the brilliant X-ray glow that observatories like Chandra can map. In these images, we can literally see the stolen fuel, a shimmering cloud of million-degree plasma that tells the tale of galactic robbery. Untangling which of these fates dominates and when is the challenge of mapping the Baryon cycle. It requires astronomers to use the full spectrum of light, from radio waves that trace cold molecular gas, to infrared light that sees dust, to optical light for the stars, and up to X-rays for the superheated plasma. Only by combining these views can we see the complete picture of inflow, transformation, and outflow. It reveals a galaxy not as an island, but as a dynamic ecosystem constantly exchanging matter with its surroundings. The silence of a dead galaxy, then, is the sound of this cycle finally breaking down, the flows stopping, and the great cosmic engine of creation winding to a permanent halt. But this visible story of gas, stars, and black holes is only part of the picture. The true architect of a galaxy's destiny is something we cannot see at all. Every galaxy, from the smallest dwarf to the largest elliptical, is embedded within a vast, invisible cocoon of dark matter. This mysterious substance, which neither emits nor reflects light, makes up the overwhelming majority of a galaxy's total mass. It is the hidden skeleton, the gravitational scaffolding upon which the entire luminous structure is built. Without this dark matter halo, a galaxy like our Milky Way would simply fly apart, its stars scattered into the void by their own orbital speeds. This invisible framework was present from the very beginning, its gravitational pull acting as a cosmic seed around which ordinary gas could accumulate, cool, and eventually ignite into the first stars. It dictates the overall shape and size of the galaxy that forms within it. Yet, dark matter's role in a galaxy's life and death is subtle and indirect. It does not participate in the nuclear fusion that lights stars, nor does it interact with the fierce radiation from black holes. Its influence is purely gravitational, a steady, pervasive pull that sets the stage for everything else. The distribution and evolution of this dark matter halo profoundly affect how a galaxy lives and ultimately how it dies. The rate at which fresh, cold gas can flow into a galaxy from the cosmic web is governed by the gravity of its dark matter halo. A massive, healthy halo acts like a deep gravitational well, steadily funneling new fuel into the galactic center to sustain star formation over billions of years. However, this beneficial relationship has a tipping point. As a galaxy grows and its dark matter halo reaches a critical mass, the very process of gas inflow can become its undoing. The enormous gravitational potential can compress infalling gas so violently that it triggers an extreme, unsustainable burst of star formation, rapidly depleting the fuel reserves. More importantly, such a massive halo is more likely to host an equally massive central black hole. When that black hole feeds, the resulting feedback can be catastrophic, easily heating or expelling the galaxy's gas because of the immense gravitational depth it must escape from. In this way, the dark matter halo sets the upper limit for a galaxy's growth and activity. Reaching that limit often marks the beginning of the end for its star-forming era. The environment can also attack this invisible scaffold. When a galaxy falls into a dense cluster or has a close encounter with a neighbor, it can experience tidal stripping. Just as the visible stars and gas can be pulled away, the extended dark matter halo itself can be sheared off by the immense gravitational tides. This loss of the invisible scaffolding weakens the galaxy's gravitational grip on its own remaining gas, making it far easier for processes like ram pressure stripping to rob it completely. A galaxy stripped of its dark matter halo is like a tree whose roots have been severed. It may stand for a while, but it is cut off from its source of sustenance and stability, destined to wither. So, while we watch the visible universe fade from blue to red, the ultimate script for that transformation is written in the unseen. The mysterious dark matter, which constitutes the overwhelming majority of every galaxy, creates the conditions for both brilliant life and long, silent death. It is the silent partner in every cosmic story, its invisible hand guiding the fate of all the light we can see. The cosmic timeline holds a startling secret, a paradox that rewrites our understanding of galactic life cycles. Deep within the ancient light of the early universe, astronomers have found galaxies that died long before their time. While most models suggest a gradual, multi-billion-year decline, these cosmic anomalies underwent a rapid and premature transformation into silence, becoming celestial fossils when the universe was still in its relative youth. They challenge the very notion of a slow, inevitable fade, forcing us to ask, why do some galaxies die early? The discovery came as a profound surprise. By peering back to when the universe was only about 3 or 4 billion years old, a mere fraction of its current age, telescopes like Hubble began to pick out small, dense, and astonishingly red galaxies. They were not the vibrant, star-forming spirals expected in that energetic epoch. Instead, they were compact, massive, and already quiescent, having shut down their star formation engines in a cosmic blink. Astronomers nicknamed them red nuggets, a term that captures both their diminutive apparent size and their dense, ancient nature. These are not the faded giants of today, like Messier 87. They are the relics of a different, more violent era of cosmic history. Their existence poses a fundamental question. How could a galaxy burn through its entire supply of star-forming gas or render it permanently unusable in such a short period? The answer seems to lie in their extreme compactness and the uniquely intense conditions of the early universe. A red nugget galaxy packs a stellar mass comparable to our Milky Way into a volume 100 times smaller. This creates an incredibly dense and energetic environment where stars are crowded together and gravitational interactions are fierce. In such a pressurized system, the processes that can quench a galaxy are not just present, they are supercharged. Star formation, if it ignites, could be explosively intense but incredibly brief, a firestorm that consumes the available fuel in a frenzy. More importantly, the supermassive black hole at the heart of such a dense galaxy would have a vast feast of gas readily available. Feeding in this environment would be like pouring fuel on a bonfire. The resulting active galactic nucleus would likely be phenomenally powerful, unleashing feedback so violent it could blow the galaxy's remaining gas clear out in a single catastrophic event. The galaxy's own brilliant, energetic heart would, in essence, commit a form of galactic suicide, sterilizing its home in one swift, decisive act. This rapid quenching pathway reveals that the journey to silence is not one single road, but a network of possibilities shaped by a galaxy's initial conditions and the era in which it lives. The early universe was a more chaotic, gas-rich, and energetic place, allowing for these accelerated life stories. A red nugget is a galaxy that lived fast and died young, reaching its final, quiet state billions of years before most of its peers even began to decline. Studying these ancient relics is like finding a perfectly preserved artifact from a lost civilization. They provide a critical test for our theories of galaxy formation, showing that under the right, or rather the extreme, conditions, the slow transformation into cosmic silence can be startlingly fast. They remind us that a galaxy's fate is not just a function of time, but of its internal structure and the unique physics of its birth era, proving that in the cosmos, even death can arrive on a dramatically accelerated schedule. This shift from brilliant blue to deep crimson is more than just a change in hue. It is the galaxy's final confession of age. The vibrant blue light that once defined a youthful, star-forming galaxy comes almost entirely from its most massive and shortest-lived citizens. These stellar giants burn with a fierce, white-hot intensity, but they are cosmic mayflies, exhausting their nuclear fuel in just a few million years. When a galaxy's star formation ceases, these brilliant blue lights are the first to go out, and they are not replaced. What remains is a population of far more patient stars. Sun-like stars which shine with a steadier yellow-white light for billions of years, and especially the countless red dwarfs, the smallest and most frugal stars, which glow with a cool, ruddy light for trillions of years. As eons pass, the collective glow of the galaxy is increasingly dominated by these longer-lived, cooler stars. The integrated color we see from a distance slowly drains of its blue vitality, shifting through gold and orange before settling into that distinctive, uniform red. This is not a rapid sunset, but a fade so gradual it is imperceptible across a human lifetime, a transformation that requires the patience of the cosmos itself to witness. For astronomers, this color is a powerful forensic tool. By carefully analyzing the precise shade of red and the specific wavelengths of light present in a galaxy's spectrum, they can perform a kind of cosmic archaeology on its stellar population. They can model the mix of stars, estimating the ages of the last generation of stars to form. This allows them to essentially carbon date the galaxy's death, determining not just that it is quiescent, but approximately when its star-forming era came to an end. A galaxy that appears a deep, pure red likely ceased forming stars many billions of years ago, its stellar population having aged in unison for eons. A galaxy with a more orange or yellowish tinge might be a more recent arrival to the red sequence, its last burst of star formation a mere few billion years in its past. This simple act of reading color becomes a way to map the history of cosmic silence across the universe, tracing which galaxies died first and which held on to their vibrant youth a little longer. The visual metaphor is profound. The blue of a star-forming galaxy is the color of action, of birth, of intense energy. The red of a quiescent galaxy is the color of embers, of stability, of a long, slow coasting toward an inevitable end. It is the universe's own visual language for life and afterlife, written in the combined light of hundreds of billions of suns. Watching this color transition across vast populations of galaxies is like watching a forest change with the seasons, but on a scale where a single season lasts for cosmic epochs, a slow turning of the page from a chapter of furious creation to one of profound and lasting quiet. Between the stark divide of vibrant blue and silent red, a subtle but crucial middle ground exists. This is the cosmic green valley, a sparsely populated region in the color magnitude diagram where galaxies are caught in the act of transformation. They are neither fully alive with star formation nor completely dead and red. Instead, they glow with an intermediate hue, often a pale greenish or yellowish light, a visual signal that their stellar populations are in flux. These galaxies are the missing link, the crucial transitional phase that captures the slow strangling of a galaxy's creative heart. They are not permanent residents of this valley, but travelers passing through on a one-way journey from the blue cloud to the red sequence. Their very existence confirms that galactic death is not an instantaneous switch, but a process, a slow fade that can be observed and measured. Studying a galaxy in the Green Valley is like finding a patient in the middle of a long illness, their vital signs changing, offering doctors clues about the progression of the disease. For astronomers, these objects are priceless laboratories. By analyzing their light, researchers can determine the rate at which their star formation is declining. They can search for the fingerprints of the quenching mechanism at work, whether it's the faint glow of heated gas from black hole feedback, the telltale signatures of stripped gas from environmental forces, or simply the exhausted glow of a fuel tank running dry. The Green Valley holds the key to timing the great cosmic fade, revealing whether a galaxy's star-forming engine sputters out over a few 100 million years or languishes in decline for several billion. This leads to one of the valley's deepest mysteries. Why is it so sparsely populated? If the transition takes a long time, we would expect to see many galaxies lingering in this intermediate state. The fact that we see relatively few suggests that for many galaxies, the passage through the Green Valley is surprisingly swift. Once the quenching process is triggered, it may accelerate, pushing the galaxy rapidly toward its red and dead fate. This points to a feedback loop where the decline of star formation creates conditions that hasten the decline further. Perhaps as star formation slows, less supernova energy is produced to stir and heat the gas, but the central black hole, having been fed during a prior merger, finally unleashes its delayed feedback, delivering the final, decisive blow to the remaining fuel. Alternatively, a galaxy may linger in the Green Valley if its quenching is gentle, a slow exhaustion rather than a violent expulsion. The speed of the transition through this valley is a direct clue to the cause of death. A galaxy stripped by its cluster environment might race through, while one slowly starving from within might take a more leisurely path. This makes Green Valley galaxies prime targets for the next generation of observatories, like the James Webb Space Telescope and future giant ground-based telescopes. These instruments will peer into their hearts with unprecedented detail, mapping their remaining gas, pinpointing the locations of any final star-forming regions, and directly imaging the effects of feedback from their central black holes. They will transform these faint, transitional objects from statistical points on a graph into richly detailed portraits of cosmic change. The Green Valley, therefore, is not just a waypoint on a chart. It is the active crime scene of galactic death. By solving its mysteries, we move closer to answering the ultimate question, not just how galaxies die, but what specific sequence of events writes the final chapter for each unique island of stars in the dark ocean of space. The final, enduring citizens of a silent galaxy are not stars in the true sense, but their extraordinary remains. After the last red dwarf has finally flickered out, the galactic landscape will be dominated by three classes of stellar relics, each more extreme and faint than the last. The most common will be white dwarfs. These are the Earth-sized cores left behind when sun-like stars shed their outer layers. Incredibly dense, a single teaspoon of white dwarf material would weigh as much as an elephant here on Earth. They are not powered by fusion, but glow faintly with the leftover heat of their creation, destined to cool over tens of billions of years into cold, dark cinders known as black dwarfs. No black dwarf is believed to exist yet in our universe, as the process of cooling to absolute darkness takes longer than the current age of the cosmos. They represent the ultimate fate of the vast majority of stars, a slow fade into complete invisibility. For stars that began their lives with more mass, the end is even more dramatic. When these giants explode as supernova, their cores can collapse into a neutron star. Imagine compressing the mass of our entire sun into a sphere the size of a city. The result is matter so unimaginably dense that atomic structure itself is crushed, leaving behind a sea of neutrons. A sugar cube of neutron star material would weigh as much as a mountain range. Some of these objects, called pulsars, spin rapidly, beaming out lighthouse-like pulses of radio waves as they rotate. Yet even these brilliant signals are fleeting on cosmic timescales as the spin gradually slows and the beams grow faint. The final class of remnant is born from the most massive stellar collapses of all, where the core's gravity is so overwhelming that not even the pressure of neutrons can withstand it. The collapse continues unchecked, forming a stellar mass black hole, a region of space where gravity is so intense that nothing, not even light, can escape. It is a perfect sink, a one-way door from our universe. Together, this population of relics defines the galaxy's final phase. White dwarfs slowly dimming to blackness, neutron stars spinning down into silence, and black holes sitting in utter darkness. They emit virtually no new light, only slowly radiating away their residual heat or gravitational energy. The combined glow of the galaxy, once a brilliant tapestry of billions of fusion-powered suns, diminishes to a faint infrared whisper and then to near nothingness. This is the true onset of the cosmic silence heralded by the red sequence, a darkness not of empty space, but of a space filled with invisible, inert monuments to a vibrant past. The galaxy becomes a museum of extreme physics, a graveyard of gravity's ultimate victories, where the stories of stellar life are frozen forever in these bizarre, silent forms. But is this cosmic silence truly a one-way street? The stark division of the color magnitude diagram and the overwhelming trend toward quiescence suggest a finality to galactic death. Yet nature is rarely so absolute. Against the backdrop of this grand fade, astronomers have begun to spot rare and fascinating exceptions, galaxies that appear to defy their own fate. These observations lead us to the eighth mystery: can a dead galaxy be rejuvenated? The answer, while complex, hints at a universe that still holds surprises in its oldest corners. Rejuvenation is not about reversing time, but about a temporary, dramatic resurgence of star formation in a galaxy that had long been quiet. The mechanism is almost always external, a sudden and violent gift of fresh fuel. Imagine a dormant forest, its soil depleted and its trees ancient, being suddenly flooded by a nutrient-rich river from a distant storm. For a red and dead galaxy, that river is cold, dense gas. This new fuel can arrive through several cosmic channels. A minor merger, where a small, gas-rich dwarf galaxy is devoured by the larger quiescent giant, can inject a fresh supply of star-forming material directly into its heart. Alternatively, the galaxy might, through its slow drift across the cosmos, plow into a previously untouched filament of the cosmic web, a vast primordial reservoir of pristine hydrogen gas. Even a strong tidal interaction with a passing neighbor without a full merger can destabilize and compress any tiny, lingering reservoirs of gas within the galaxy, potentially sparking a final, brief burst of creation. We see evidence of this in a small population of galaxies that appear to be red and dead at their cores, yet show faint, delicate rings or shells of blue star formation at their outer edges, like a final, defiant bloom on an ancient tree. These are the signatures of a recent minor accretion event, a last gasp of cosmic creativity. However, these events are almost always short-lived. The galaxy's internal conditions have not changed. Its supermassive black hole, though dormant, is still present and ready to be fed. The fresh infusion of gas can quickly trigger that black hole back into activity, leading to a new round of fierce feedback that heats or expels the new fuel. Or if the galaxy resides in a harsh cluster environment, the same ram pressure forces that stripped it before will quickly act on this new gas as well. The resurgence is a fleeting phenomenon, a temporary reversal in a long-term trend. The galaxy may blaze with a new generation of blue stars for a few 100 million years, but it will almost certainly settle back onto the red sequence, its journey into silence merely interrupted, not rewritten. This raises the profound question of true rejuvenation versus temporary resurgence. Is there any mechanism that could permanently restart the star-forming engine of a galaxy that has been quiescent for billions of years? On the timescales of the current universe, the answer appears to be no. The balance has shifted too far. The galaxy's dark matter halo may have grown too massive, making feedback too efficient, or its environment too hostile. Yet, on the longest imaginable timescales, in the distant Degenerate era, even stranger possibilities might emerge. If two entirely quiescent elliptical galaxies, each devoid of gas, were to merge over an epoch of trillions of years, the sheer gravitational violence of the collision could, in theory, tear stars apart. This would release a small amount of gas and dust back into the mix, potentially allowing for a single, final generation of stars to be born from the ashes of the old. This would be a rebirth from stellar death itself, a cycle so slow and rare it borders on the mythological. For now, these rare resurgences teach us that galactic death is not an event, but a dominant tendency, a gravity well of silence that is incredibly difficult to escape. They show us that while the universe's story is one of increasing quiet, it still contains pockets of unexpected and beautiful rebellion, brief flickers of blue light in the growing red dark. The ultimate silence of individual galaxies is merely the opening act for a far grander, darker cosmic play. To grasp the final destination of this journey, we must stretch our imagination across a timeline that dwarfs all of human history, a future so distant it is measured not in billions, but in trillions of years. This is the Degenerate era, a phase that will begin long after the last red dwarf star has finally exhausted its fuel. In this era, the universe will no longer be lit by the steady fire of nuclear fusion. The brilliant cities of stars will have transformed into dark museums of exotic physics. Galaxies will still exist as gravitational structures, but they will be populated almost entirely by stellar remnants, the silent relics of a bygone age of light. Countless white dwarfs, now cold black dwarfs, will drift like invisible cinders. Neutron stars will have spun down to a near halt. Stellar mass black holes will wander the darkness. And at the center of it all, the supermassive black holes will sit in profound dormancy, their immense gravity the only remaining sign of their once dominant presence. The only significant sources of energy in this era will be the faint, residual heat slowly leaking from these cooling remnants, and an even more esoteric process predicted by theoretical physics, Hawking radiation. This is the theoretical, incredibly slow evaporation of black holes, where they are thought to emit particles and gradually lose mass over timescales so vast they are almost meaningless to our minds. Even this faint whisper of activity is not eternal. The degenerate era will eventually give way to the black hole era as the last white dwarfs and neutron stars fade to absolute zero, and the only objects of significant mass remaining are the black holes themselves. The cosmos will be a scattering of these dark titans in an ever-expanding, ever-cooling void, and then, on a timescale so long it defies comprehension, even the black holes will not last. Through the glacial process of Hawking radiation, the stellar mass black holes will evaporate first, in perhaps 10 to the power of 67 years, followed eons later by the supermassive giants. Their disappearance will mark the beginning of the dark era, or the heat death of the universe. What remains will be a sea of isolated subatomic particles and photons, stretched so far apart by the expansion of space that interactions become vanishingly rare. The universe will approach a state of maximum entropy, thermodynamic equilibrium, where no energy can be harnessed to do work and no new structures can ever form. It will be a cosmos of near total darkness, cold and silence. This speculative, almost philosophical endpoint frames the death of galaxies in a startling new light. The slow reddening and quieting we have traced is not the end of the story, but merely the closing of its most vibrant and creative chapter. It is the transition from a universe rich with complexity and light to one of simplicity and dark. Understanding this ultimate fate does more than satisfy our curiosity. It reshapes the meaning of our present moment. We are living in the cosmic spring, a fleeting golden age of star formation and galactic brilliance that occupies just a tiny sliver of the universe's entire timeline. The grand spirals, the glowing nebulae, the very possibility of planets like ours, all exist within this narrow window of cosmic opportunity. This knowledge instills a profound sense of rarity and preciousness. It suggests that the era of life and observation may be a unique and temporary phenomenon in the grand narrative of the cosmos. Our quest to understand galactic death, therefore, becomes more than an astronomical study. It is an act of cosmic awareness, a way to comprehend the full arc of the story in which we are briefly, miraculously present. The silent, red galaxies we see today are not just endpoints. They are messengers from the future, showing us the quiet destiny that awaits all islands of light, and in doing so, they illuminate the incredible, transient beauty of the epoch we call home. This violent creativity carries a hidden price, one that often leads to the very silence we seek to understand. Major mergers between galaxies are among the most dramatic events in the cosmos, capable of both igniting brilliant firestorms of new stars and, paradoxically, ensuring a galaxy's permanent quietude. This duality lies at the heart of galactic cannibalism, where a larger galaxy consumes a smaller companion. The outcome of this cosmic feast is not predetermined, but depends on a delicate recipe of ingredients and conditions. The most critical ingredient is the gas content of the two galaxies involved. If both are rich in cold, dense fuel, the collision violently compresses those gas clouds, triggering a spectacular, widespread burst of star formation. For a time, the merging system becomes a dazzling starburst galaxy, shining with the light of billions of newborn suns. Yet, this fertile frenzy is often self-limiting. The same gravitational turmoil that compresses the gas also funnels vast rivers of it directly into the supermassive black holes at the galaxy's cores. This ignites them as brilliant quasars or unleashes powerful jets, flooding the system with energy that heats the remaining gas to millions of degrees, rendering it useless for future star formation. The merger, in its glorious violence, can effectively sterilize its own environment. The final product of such a gas-rich merger is often a smooth, featureless elliptical galaxy, its spiral structure forever scrambled by the gravitational chaos. It is left gas-poor and quiet, its stellar population left to age in unison toward that deep, uniform red. But what if the devoured galaxy is already gas-poor, a quiet, red nugget itself? In that case, the cannibalism is a dry merger, a collision of stars and dark matter with little new fuel to add. This does not spark a new era of star birth, but simply builds a larger, redder elliptical galaxy, a silent giant grown through the accumulation of other silent giants. This process helps explain the stunning diversity we see within the red sequence itself. Not all dead galaxies are identical. Some are compact red nuggets, relics of the early universe's rapid quenching. Others are mid-sized ellipticals, perhaps the results of quieter mergers, and at the top are the behemoths like Messier 87, which sit at the centers of galaxy clusters, having grown to immense size through a long history of cannibalizing smaller neighbors. Each merger leaves an archaeological signature, faint streams of stars or vast halos of globular clusters that tell the tale of its violent growth. So galactic cannibalism reveals a profound cosmic truth, that violence and silence are not opposites, but can be successive chapters in the same story. A merger can be the brilliant, final act of a galaxy's creative life, a climax that exhausts its potential and ushers in an eon of quiet. This helps us see the red sequence not as a monolithic graveyard, but as a gallery of final forms, each shaped by its own unique history of collisions, feasts, and transformations, all leading to the same destination of cosmic silence. The silent transformation of galaxies from blue to red is not witnessed by any single eye, but by a vast, interconnected network of artificial ones, each designed to see a different piece of the cosmic puzzle. Modern astronomy has moved far beyond simply cataloging points of light. To understand a galaxy's slow fade, scientists must become cosmic coroners, using specialized tools to determine the cause and timing of death by examining the body in every wavelength of light it emits. Optical telescopes like the legendary Hubble and its successor, the James Webb Space Telescope, serve as the primary investigators of starlight itself. They capture the beautiful images we see, but their true power lies in spectroscopy. By splitting a galaxy's light into a rainbow of colors, astronomers can read its spectral fingerprint. This reveals the precise mix of young, blue stars and old, red stars, allowing them to date the last major burst of star formation and confirm whether a galaxy is truly quiescent. The stark division between the blue cloud and the red sequence was first mapped in breathtaking detail by massive surveys like the Sloan Digital Sky Survey, which robotically scanned the sky to chart the positions, colors, and spectra of millions of galaxies, creating a cosmic census that revealed the large-scale patterns of life and death across the universe. But starlight only tells part of the story. To find the missing fuel, astronomers turn to radio telescopes. These immense dishes are tuned to listen for the faint whispers of cold molecular hydrogen gas, the raw material for stars. In a vibrant, star-forming galaxy, radio maps show this cold gas concentrated in bright clouds along spiral arms. In a galaxy undergoing quenching, these maps may show the gas being violently displaced, blown away by winds, or simply absent, providing direct evidence of the crime. For the hot gas, the superheated plasma that results from feedback or environmental stripping, a completely different tool is required: X-ray observatories like the Chandra X-ray Observatory. These instruments see the high-energy glow of million-degree gas, revealing the vast halos around galaxies or the brilliant cores of active black holes. They show us where the galaxy's lifeblood has been heated to a state of permanent uselessness. The latest revolution comes from instruments called integral field units. These remarkable devices attached to large telescopes don't just take a picture or a single spectrum, they take thousands of spectra across a galaxy's face simultaneously. This creates a detailed data cube, a three-dimensional map that shows where star formation is still sputtering, where gas is being heated, and where jets from a central black hole are impacting the surrounding material. It transforms a distant smudge of light into a rich, dynamic portrait of a galaxy in transition. All these mountains of observational data are then fed into sophisticated computer simulations. These are not video games, but rigorous mathematical models that simulate the laws of physics, gravity, hydrodynamics, and radiation across billions of years. Astronomers can test different quenching scenarios, running virtual universes to see which models produce galaxies that match the colors, shapes, and gas content we actually observe. It is a constant dialogue between discovery and theory, where a new observation from a telescope can challenge a simulation, and a puzzling result from a simulation can guide where we point our telescopes next. This entire technological symphony turns the philosophical concept of cosmic silence into a rigorous, data-rich field of study. We are no longer just watching the lights go out. We are learning to read the detailed autopsy report of each galaxy, uncovering the specific sequence of events that led to its long, quiet rest. The story of galactic death changes dramatically when we shift our gaze from the titans to the smallest citizens of the cosmos. Dwarf galaxies, containing merely a few billion stars compared to the hundreds of billions in a spiral like our Milky Way, follow a different, often more fragile, evolutionary path. Their small size and shallow gravitational wells make them exquisitely sensitive to their surroundings, turning their lives into case studies of cosmic vulnerability. Some of these tiny systems faced a brutal end in the universe's infancy. During the epoch of reionization, when the first brilliant stars and galaxies flooded the cosmos with intense ultraviolet radiation, that harsh light could heat and evaporate the scant gas reserves of the smallest dwarfs. This process may have quenched them almost immediately, leaving behind ultra-faint dwarfs we see today as ghostly collections of ancient stars, fossils from the dawn of time that never had a chance to truly thrive. For those that survived that early trial, environment is everything. A dwarf galaxy orbiting a massive spiral like our own is subject to relentless tidal forces, its shape stretched and distorted with each close pass. More devastatingly, if it ventures through the disk of its giant host or the hot halo surrounding it, its meager gas can be stripped away in an instant through ram pressure. This leaves behind a dark matter-dominated relic, a galaxy that is essentially all skeleton with no flesh, its stars left to age without any future generations. In the crowded violence of a galaxy cluster, this fate is almost a certainty, with dwarfs being rapidly transformed into silent, red spheroids. Yet there exists another possibility for the fortunate few. A dwarf galaxy that lives in profound isolation, far from any massive neighbor or cluster, may avoid these catastrophic encounters. In such a quiet backwater of the universe, with its shallow gravity unable to drive rapid star formation, it might settle into a state of incredibly slow, sporadic creation. It could form a handful of new stars every billion years, a faint, intermittent pulse of life that stretches on for epoch after epoch. This presents a profound mystery that challenges our very definitions. If a galaxy never fully shuts down, but merely reduces its star formation to a barely detectable trickle, has it truly died? Or is it simply living life on a different, almost geological timescale? These isolated dwarfs suggest that the boundary between life and death for a galaxy is not a bright line, but a vast gray expanse of near silence. Their potential for indefinite, low-level activity forces us to reconsider the finality we so easily assign to the majestic red giants. On the smallest scales, the cosmic story may not be one of an inevitable fade to black, but of an enduring, faint whisper of light, persisting in the quietest corners of the universe long after the great cities of stars have gone dark. The profound silence awaiting every galaxy is more than an astronomical fact. It is a mirror held up to our own existence. Contemplating these cosmic endings forces us to confront the nature of impermanence on a scale that stretches the limits of human comprehension. Our entire recorded history, the rise and fall of empires, the lifespan of our species, and the very age of our planet are less than a single heartbeat in the multi-billion-year narrative of a galaxy's life and slow fade. From this vantage point, human civilization appears as the most fleeting of sparks, a brief, bright flicker in an ocean of darkness that has existed for eons and will persist for eons more. This realization can initially feel overwhelming, evoking a deep sense of our own smallness. Yet, within that feeling lies a transformative shift in perspective. Our apparent insignificance in space and time is not a verdict of meaninglessness, but an invitation to a deeper connection. We are not separate observers looking in on a cold, distant universe. We are products of it. The atoms that form our bodies were forged in the hearts of massive stars that lived and died long before our sun was born. We are, in the most literal sense, the universe awakening to contemplate itself. Our ability to trace the life cycles of galaxies, to piece together stories from ancient light, and to project a future of cosmic silence is itself a staggering achievement. It represents a consciousness capable of reaching across billions of light years and billions of years to understand its own origins and ultimate context. This cosmic viewpoint does not diminish our story, it enlarges it. We become participants in a grand narrative of unimaginable scale, a narrative of transformation from simplicity to complexity and back toward a final, simple quiet. Embracing this perspective fosters a profound humility, certainly, but it also cultivates a powerful sense of wonder and even responsibility. The knowledge we gather about these distant, fading giants is a testament to curiosity and resilience. In a universe trending toward silence, the act of seeking understanding, of bearing witness to these epic tales, becomes a profound source of meaning. We find purpose not in permanence, which the cosmos itself denies, but in the journey of discovery. By learning to read the history written in starlight, we connect our brief, brilliant moment of awareness to a saga that transcends all individual lives, finding our place not as the center of the story, but as its conscious, wandering chapter. While gravity sculpts the grand architecture and black holes deliver the final verdict, a far more subtle force weaves through the entire tapestry of a galaxy's life and death. This is the galaxy's magnetic field, an invisible, pervasive web of energy that threads between stars, coils through nebulae, and stretches across the vast interstellar voids. We cannot see it directly, but its influence is everywhere, a quiet conductor orchestrating the flow of the cosmic symphony. These fields are generated by the churning motions of ionized gas and the dynamo action of stars themselves, creating a complex, large-scale structure that can shape a galaxy's fate in profound, yet easily overlooked ways. In the vibrant chaos of a star-forming galaxy, magnetic fields act as both a scaffold and a restraint. They provide pressure that can support giant molecular clouds against their own gravity, slowing their collapse and regulating the pace at which new stars are born. They channel the flows of gas along invisible lines, guiding material into stellar nurseries or funneling it away. When massive stars explode as supernova, the magnetic field can shape and direct the expanding shock waves, influencing how much energy is deposited into the surrounding medium and how efficiently that gas is heated or blown away. It is a force that permeates every stage of a galaxy's creative cycle, a hidden hand guiding the dance of matter and energy. As a galaxy begins its slow journey toward silence, the role of its magnetic field may become even more critical, yet more enigmatic. In the quenching process, when feedback from supernova or a central black hole floods the galaxy with energy, magnetic fields can influence how that feedback propagates. They might help confine and direct the furious jets from an active galactic nucleus, making them more efficient at heating gas to extreme temperatures over vast distances. Conversely, magnetic pressure could provide a form of invisible support to pockets of residual gas, helping them resist complete expulsion and instead remain trapped in a hot, diffuse state, permanently unavailable for star formation but still part of the galaxy's atmosphere. The fields could even affect how efficiently ram pressure stripping operates in a cluster environment, either allowing gas to be more easily torn away or providing a tenuous magnetic shield that offers a faint degree of protection. Understanding this magnetic influence is like trying to listen for a single, soft instrument in the roar of a cosmic orchestra. The challenge is immense because we cannot directly photograph a magnetic field in a distant galaxy. Instead, astronomers must become detectives of polarized light. When light from stars or radio waves from cosmic rays passes through a magnetized medium, its orientation can become subtly aligned or polarized. By meticulously measuring this faint polarization across the face of a galaxy, scientists can painstakingly map the direction and infer the strength of its magnetic web. This is a frontier of observational astronomy, requiring incredibly sensitive instruments and vast amounts of telescope time. Each new map adds a crucial layer to our understanding, revealing that magnetic fields are not a minor detail, but a fundamental component of galactic ecology. They represent the 11th mystery in our quest to understand cosmic silence, a subtle but pervasive force that may gently steer a galaxy's final transformation, ensuring that when the last lights fade, they do so under the influence of an invisible, enduring order. These silent giants of the cosmos have a digital counterpart, born not from gas and gravity, but from lines of code and pure mathematics. To truly test our theories of galactic life and death, astrophysicists have built entire universes inside supercomputers. This is the realm of computational cosmology, where we don't just observe the past, we can simulate it forward and backward, watching the cosmic story play out from the first flickers of light to the final fade. Projects with names like Illustris TNG and EAGLE are not video games. They are some of the most complex scientific experiments ever conceived. They begin with the initial conditions of the early universe, a near-uniform sea of dark matter and primordial gas, and then set in motion the immutable laws of physics. The code must account for the relentless pull of gravity on both dark and visible matter, the complex fluid dynamics of swirling, heated gas, the ignition of stars within dense clouds, and the explosive feedback when those stars die or when supermassive black holes awaken. Running these simulations requires staggering computational power, often consuming millions of processor hours to model a cosmic volume, just a fraction of the observable universe over its entire 13.8 billion-year history. The goal is breathtakingly ambitious: to grow a virtual cosmos that, when we look at it statistically, mirrors the one we see through our telescopes. The payoff is a revelation. We can sit back and watch a galaxy form from nothing, see its spiral arms emerge, witness its central black hole flare to life, and then, in many cases, observe as its star formation is slowly quenched. We can rewind the simulation and ask specific questions. What if we turned off the feedback from supernova? The virtual galaxy might form stars too quickly, becoming a bright blue disk that doesn't match reality. What if we silenced the black hole? The galaxy might never quench, retaining its gas and youthful color far too long. By tweaking these parameters, scientists can isolate which physical processes are essential to produce the cosmic landscape we inhabit, particularly the stark divide between the blue cloud and the red sequence. These digital laboratories have been instrumental in revealing how the delicate, often violent, interplay between dark matter scaffolding, gas dynamics, stellar birth, and black hole fury leads to the diverse fates of galaxies. They show us that no single force is responsible, but rather a chorus of mechanisms that can dominate at different times or in different environments. A simulated galaxy might be quenched because its gas is stripped as it falls into a cluster, or because its own black hole heats the gas from within, and the simulation lets us trace which pathway left the specific fingerprints we see. While these virtual universes are not perfect replicas, and their resolution is still too coarse to capture every detail, they provide an irreplaceable dynamic narrative. They allow us to connect a galaxy's final, silent state we observe today directly back to the events in its ancient past, transforming static snapshots into a flowing, causal story. In this digital cosmos, we have a time machine, one that lets us witness the slow transformation into silence over and over again, testing our understanding of the grandest story ever told. The universe is not just expanding, it is accelerating, driven by a mysterious force that pushes space itself apart. This is dark energy, a dominant component of our cosmos that shapes its ultimate destiny. While its effects are most dramatic on the grandest scales, its subtle influence may also be felt in the quiet fate of individual galaxies, weaving a thread that connects the local story of stellar death to the global future of everything. As dark energy accelerates the expansion of the cosmos, it steadily increases the distances between galaxies. Over billions of years, this cosmic isolation grows more profound. For a galaxy drifting in the relative emptiness of intergalactic space, this isolation has a direct consequence. It becomes cut off from the great cosmic web, the vast network of dark matter and gas filaments that once funneled fresh, cold hydrogen into galactic centers. The river of new fuel slows to a trickle and then stops entirely. This is a slow, environmental quenching on the grandest possible scale. While internal processes like black hole feedback or a galaxy's own star formation history are the immediate causes of silence, dark energy sets the long-term stage, making it increasingly difficult for a galaxy to ever replenish its spent fuel. It ensures that the dominant trend across cosmic time is toward separation and stillness. This connection transforms our understanding of galactic death. It is no longer just a story about local gravity, gas physics, and violent mergers. It becomes a narrative deeply entwined with the fundamental fabric of spacetime itself. The same force that determines the universe will expand forever also indirectly ensures that the islands within it will grow ever more isolated, their lights fading in an ever-widening sea of dark. This presents a monumental challenge for astrophysicists, linking the incredibly large, the realm of cosmology and dark energy, to the relatively small, the intricate physics within a single galaxy. It requires models that can bridge these vast scales, showing how a global push can influence a local fade. In this light, the red sequence of dead galaxies is not just a collection of individual endpoints, but a statistical signature of the universe's accelerating expansion, a cosmic trend written in the fading light of countless ancient suns. The long transformation into silence, therefore, is more than a galactic process. It is a cosmological one, a quiet echo of the universe's own relentless and accelerating drift into a cold, dark future. The faint, ruddy glow of a red dwarf is the signature of cosmic patience. In a galaxy that has long since ceased its grand star formation, these smallest of stars become the final keepers of the flame. Their brilliance is modest, a cool, deep crimson compared to the blazing blue giants of a galaxy's youth, but their endurance is unparalleled. A typical red dwarf, with a mass just a fraction of our sun's, burns its hydrogen fuel with such incredible frugality that its lifespan is measured in trillions of years. To put that in perspective, the entire universe is only around 13.8 billion years old. These stars will outlive every other type of star by orders of magnitude, persisting long after galaxies like our own have merged and faded to red. They are the ultimate survivors, destined to become the sole sources of steady light in a population of aging, dimming suns. As the eons stretch on, the collective color of a dead galaxy deepens from a golden red to a profound, uniform crimson, a direct result of these countless, faint embers outshining everything else. This era of the last stars is a chapter of profound stillness. Imagine a great forest where the oldest, mightiest trees have long since fallen, and only the most resilient, slow-growing mosses and lichens remain, covering the landscape in a muted, enduring blanket. The galaxy's dynamic heart has stopped. No new nebulae ignite, no supernova tear through the spiral arms. The once bustling stellar nurseries are empty and dark. All that remains is this patient dimming, a collective sigh as the red dwarfs continue their slow, steady fusion for time spans that defy human imagination. Their light is the last echo of the galaxy's vibrant past, a fading memory written in photons. Yet, even their incredible endurance has a limit. One by one, over trillions of years, each red dwarf will finally exhaust the hydrogen in its core. Without the outward pressure of fusion to balance the inward crush of gravity, the star will contract. It will shed its outer layers and its core will cool and crystallize, transitioning into a white dwarf, an Earth-sized cinder of degenerate matter. This transformation marks the true end of stellar luminosity for that star. Its light, which has shone for longer than the current cosmos has existed, will begin a final, slow fade to black. When the last red dwarf in a galaxy makes this transition, a profound threshold is crossed. The era of stars of fusion-powered light is over. The galaxy enters a state of near-total darkness, illuminated only by the residual heat of cooling white dwarfs and neutron stars, a faint infrared whisper against the absolute cold of space. The occasional flash might pierce this gloom, perhaps from the rare collision and merger of two such stellar remnants. If two white dwarfs spiral together, their violent union could trigger a final, spectacular supernova, a last shout in the cosmic silence. Or the slow, gravitational dance of brown dwarfs, failed stars that never ignited fusion, might produce a brief flare of infrared light. But these are isolated events, flashes in an eternal night. They are not the steady, life-giving light of a sun, but the final, random sparks from a cooling hearth. This slow fade of the last stars underscores a humbling truth about our universe. The brilliant, dynamic era of galaxies ablaze with light is not the default state of the cosmos, but a temporary, glorious phase. We live in the stellar springtime, a period of abundant energy and creation that occupies a mere sliver of the universe's potential timeline. The enduring legacy will be one of darkness and cold, a future dominated by relics and silence. The persistent glow of the red dwarfs, therefore, is a poignant bridge between these two extremes. It is a reminder that all light, no matter how long it persists, is transient on a cosmic scale. Their trillion-year vigil is our clearest window into the fate of all galactic light, a slow, beautiful, and inevitable dimming that writes the final sentence in the story of visible cosmic activity. The universe presents us with a profound and fortunate coincidence. We exist at a cosmic moment that allows us to witness the entire spectrum of galactic life and death, from vibrant birth to eternal silence, all at once. This is the gift of the finite speed of light. When we peer into deep space, we are also gazing back into deep time. A galaxy 1 billion light-years away appears to us as it was 1 billion years ago. This turns the entire sky into a time machine, and by cataloging galaxies at different distances, we can stitch together a stop-motion film of cosmic evolution spanning billions of years. We see the brilliant blue star formers of the early universe, the transitional galaxies caught in the Green Valley, and the ancient red giants that have been silent for eons. We are not just looking at different places, we are looking at different chapters in a single grand story. This ability to construct a cosmic movie from still images is one of astronomy's most powerful tools, letting us observe a process far too slow for any single civilization to witness directly. It means we are, in a very real sense, watching galaxies die right now. We are simply seeing their deaths at different moments in the past, like finding photographs of a single tree from its seedling stage, its full leafy maturity, and its final withered state, all spread out on a table before us. The challenge lies in interpreting this album correctly. Is the sequence we piece together the only story, or are we seeing multiple parallel narratives? Does every galaxy follow the same basic script from blue to red, or are there many different genres of galactic life, each with its own pacing and final act? The evidence suggests a complex answer. The clear bimodal distribution of galaxies into the blue cloud and red sequence tells us the endpoints are well defined, but the pathways between them are diverse. Some galaxies, like the ancient red nuggets, seem to have taken an express route to silence in the universe's youth. Others, like our own Milky Way, are on a slower, more scenic path that includes a dramatic merger as a final, brilliant climax before the long fade. Still others in dense clusters may have had their futures violently stolen from them by their environment. Our cosmic movie is not a single film strip, but a multiplex theater playing many different films simultaneously. The great task of modern astrophysics is to sort these films into genres, to understand which quenching mechanisms dominate in which environments and eras. Are we, by sheer luck, living in a special time that makes this all visible? In many ways, yes. If we existed in the far future during the Degenerate era, the sky would be largely dark with only the faint, cool relics of stars. The vibrant story of galactic transformation would be over, its evidence grown too dim to easily read. Conversely, if we existed in the very early universe, we would see only the first brilliant bursts of star formation, with no red sequence to hint at the quiet destiny awaiting every island of light. Our present epoch is a cosmic sweet spot, a golden age of observation where the universe is old enough to have produced a rich diversity of galactic forms, yet young enough that their light still reaches us in abundance. We are living in the universe's afternoon, a time of mature complexity where we can trace both the vibrant growth of spring and the coming autumn of silence in the same glance upward. This privileged vantage point is not just a lucky break for scientists, it is an invitation to cosmic awareness. It allows us to understand our place within a dynamic, evolving cosmos, to see that the galaxies are not eternal fixtures, but characters in an epic narrative with a beginning, a middle, and a long, quiet end. We are the witnesses to this story, and our very ability to piece it together from fragments of ancient light is a testament to the curious, persistent spark of consciousness in a universe slowly, inevitably turning out the lights. This human impulse to find patterns in the cosmos is ancient and profound. Long before telescopes, our ancestors looked to the night sky and wove stories from the stars, narratives that sought to explain the origins of the world and its inevitable transformations. The great myths of creation, destruction, and renewal that echo across countless cultures are not so different from the astrophysical story we are telling today. They are humanity's first attempts to understand cosmic cycles, to grapple with impermanence on a grand scale. The Norse myth of Ragnarok tells of a great battle leading to the death of the gods and the submersion of the world in water, only for a new green earth to rise again. The Hindu cosmology describes cycles of creation, preservation, and dissolution, with the universe breathing in and out over eons. The phoenix, a legendary bird that cyclically regenerates by rising from its own ashes, is a symbol found from ancient Egypt to classical antiquity. These are not mere fantasies, they are profound reflections on the nature of existence, on the truth that all things, even the seemingly eternal, are subject to change and rebirth. In this light, the scientific narrative of galactic death and cosmic silence becomes a modern myth, a story grounded in data and observation, yet carrying the same thematic weight. It speaks of a brilliant golden age of stellar creation, a period of mature stability, and then a long, slow fade into a different state of being. It is a story of transformation, not annihilation. The galaxy does not vanish, it transitions, just as the phoenix's end is the necessary precursor to its new beginning. This parallel enriches our understanding of both science and story. It shows that the human drive to find meaning in the vastness is a constant. Our ancient myths used gods and monsters to personify cosmic forces, while our modern science uses mathematics and physics to model them. But the underlying awe and the fundamental questions remain strikingly similar. What is our place in this grand scheme? How do we find meaning in the face of impermanence? The story of galactic death provides a scientific framework for these timeless human inquiries, allowing us to see our own fleeting moment of consciousness as part of a narrative that spans billions of years. This interdisciplinary perspective beautifully bridges the sciences and the humanities. It reveals that the astrophysicist charting the red sequence and the poet contemplating mortality are engaged in a shared, deeply human project, trying to comprehend our place within a universe of constant change. Our scientific pursuit to map cosmic silence is, in a very real sense, a continuation of this ancient quest. It is a way of looking at the cold, hard facts of astrophysics and still finding a story, a narrative of grandeur, transformation, and legacy that helps us contextualize our own existence. By seeing the death of galaxies through this dual lens, we do more than understand a physical process. We connect it to the core of human experience, finding in the silent future of the stars a reflection of our own search for meaning in an impermanent world. The silent giants of the cosmos hold their histories within the very stars they contain. Unlocking these stories requires a new kind of cosmic detective work, a field known as Galactic Archaeology. This is the meticulous study of a galaxy's fossil record, not in layers of rock, but in the chemical makeup and motion of its individual suns. As our telescopes grow ever more powerful, this approach promises to reveal the most intimate details of a galaxy's life and slow death, transforming each quiescent system from a distant red smudge into a detailed historical document. The principle is beautifully analogous to geology on Earth. A geologist can examine the layers of the Grand Canyon and read a billion-year story of ancient seas, shifting deserts, and volcanic upheaval. A galactic archaeologist does something similar, but instead of rock strata, they examine the stellar population. By capturing the light from millions of individual stars within a nearby dead galaxy, scientists can perform a kind of cosmic spectroscopy on a grand scale. Each star's spectrum reveals its unique chemical fingerprint, the specific blend of heavy elements like iron, oxygen, and magnesium present in its atmosphere. This composition is a birth certificate telling us when and where that star was born. Stars that formed early in the galaxy's history from nearly pure primordial hydrogen and helium will be metal-poor. Stars born later from gas enriched by the explosions of earlier generations will be metal-rich. By mapping where the older, metal-poor stars and the younger, metal-rich stars are located within the galaxy, astronomers can reconstruct its growth. Did it form stars rapidly from the inside out? Did it acquire new populations through violent mergers? The orbits of the stars add another layer to the story. In a galaxy that grew quietly, stars tend to orbit in an orderly fashion. But if the galaxy experienced a major merger, that gravitational trauma will leave stars on chaotic, random paths, a kinematic fingerprint of ancient violence. By combining these chemical and dynamical clues, galactic archaeologists can pinpoint not just that a galaxy died, but how it died. They can determine if its quenching was a slow internal strangulation, leaving a smooth gradient of stellar ages, or a sudden, violent event like a merger, which would leave a distinct imprint of a younger, metal-rich stellar population superimposed on an older one. This turns the mystery of galactic death into a solvable historical investigation. The central question for the future is profound. As we apply this forensic technique to more and more quiescent galaxies, how many distinct evolutionary pathways will we uncover? Will every red giant tell a similar story of a central black hole's decisive feedback, or will we find a tapestry of unique endings, each shaped by a different combination of exhaustion, environment, and catastrophe? The goal is to see if these countless individual histories will converge, allowing us to write a unified theory of galactic death, a single narrative that explains the transformation of all vibrant blue spirals into silent red monuments. Or will the data reveal a cosmos even more complex, where the journey to silence is a story with countless different authors, each writing a final chapter in its own unique way? The next generation of telescopes, like the extremely large telescope being built in Chile, will be the ultimate tools for this archaeology. They will provide the light-gathering power and sharpness to perform this stellar census on galaxies tens of millions of light-years away, reading their histories star by star. We are on the verge of moving from understanding the broad statistics of galactic death to reading the detailed, personal memoirs of each silent island in the sky. The final, silent form of a galaxy possesses a profound and somber beauty. It is the aesthetic of a story completed, a light source that has settled into its last, enduring color. An elliptical galaxy, unlike the dynamic whirl of a spiral, presents a perfect symmetry, a smooth, lens-shaped glow of ancient stars that speaks of a violent past now resolved into perfect equilibrium. Its light is not the piercing blue of youth, but a deep, uniform crimson or burnished gold, a color that carries the warmth of countless aging suns. Against the absolute black of intergalactic space, this creates a visual poetry of contrast, a single island of fading warmth adrift in an infinite cold ocean. This is not the beauty of explosive creation, but of quiet resolution, a visual echo of the cosmic silence that follows the final note of a grand symphony. Artists and visualizers play a crucial role in bringing this silent phase to life for our minds, using real scientific data, from the observed colors and spectra of red sequence galaxies to the gravitational models of their dark matter halos. They create renderings that translate abstract data into emotional experience. We can see a visualization of a galaxy's last stars as points of ruby and taupe as light, slowly dimming over eons. We can watch artistic simulations of a galaxy's outer stars being stripped away by a cluster's tide, leaving delicate, fading trails like cosmic brushstrokes. These works are not mere illustration, they are interpretation, helping us feel the scale and mood of a process too slow and vast to witness directly. They allow us to appreciate the narrative not just as a graph or a dataset, but as a visual epic, a transformation of light and form that stirs a deep, reflective wonder. This intersection of art and science reveals a fundamental truth about our relationship with the cosmos. The universe's evolution is not just a chain of physical events. It is a spectacle that has always provoked awe and inspired storytelling. From the earliest star maps painted on cave walls to the breathtaking digital vistas of modern astronomy, humanity has consistently sought to frame the cosmos in terms of beauty and narrative. The silent galaxy, in its elegant, red simplicity, becomes a powerful symbol in that ongoing story. It represents an ending, yes, but an ending with dignity and a stark, majestic grace. It challenges us to find beauty not only in birth and brilliance, but in completion and quietude. To witness this aesthetic is to understand the cosmic narrative on a deeper, almost intuitive level, connecting the intellectual pursuit of how galaxies die to the timeless human capacity for wonder in the face of the sublime. The slow fade of a galaxy's light is not the only thing lost to the cosmic silence. With each star that cools into a white dwarf or collapses into a black hole, something more subtle vanishes, the intricate, organized information that defined a living stellar city. This is the 15th mystery, a question that bridges the death of galaxies to the deepest laws of physics. What happens to all that information? In a thriving spiral, information is written everywhere, in the specific orbits of billions of stars, the complex chemistry of nebulae, the delicate architectures of planetary systems, and the very pattern of spiral arms themselves. This is a galaxy's unique story, a specific and highly ordered state. As the galaxy dies, this exquisite structure dissolves. Spiral arms blur into a smooth haze. Star clusters are disrupted by gravitational tides. Planetary systems are obliterated when their host stars swell into red giants. The organized complexity that made the galaxy a dynamic, recognizable individual steadily erodes into a much more uniform, random state, a sea of aging stars and silent remnants. In physics, this relentless march toward disorder is described by entropy, a measure of a system's randomness. The death of a galaxy is, in essence, a monumental increase in entropy. The specific, low-entropy information of a living galaxy is seemingly lost, replaced by the high-entropy, generic state of a red, quiescent ellipse. This cosmic fading raises a profound paradox that touches the foundation of reality itself. According to the fundamental principles of quantum mechanics, information is never truly destroyed. It is merely scrambled or transformed. The information that described the precise state of every particle in a living galaxy should, in theory, be preserved somehow, even if it is irretrievably hidden from our view. Yet, in the classical picture of a dying galaxy, that information appears to be irretrievably dissipated, lost to the vastness of the expanding universe. This puzzle connects directly to one of the most mind-bending ideas in theoretical physics, the holographic principle. This concept suggests that all the information contained within a volume of space, like a galaxy, might be entirely encoded on its two-dimensional boundary, like a cosmic fingerprint on the surface of its event horizon. In the context of a galaxy's supermassive black hole, this hints that the information of everything that ever fell into it, every star, every wisp of gas, could be preserved on the black hole's surface, a holographic record of the galaxy's consumption. But what of the information that never crosses that horizon, the stars that simply cool and fade in the dark? Does their story vanish forever? This mystery ties the slow, majestic death of galaxies directly to the cutting edge of quantum gravity, forcing us to ask whether the universe itself has a way of remembering. Is the cosmic silence we project for the distant future not just a silence of light, but a silence of lost stories, where the specific history of every spiral arm and planetary system is erased from existence? Or does the universe, in some fundamental way we do not yet comprehend, preserve a perfect, if inaccessible, record of all that was? The death of a galaxy, therefore, is more than an astrophysical process. It is a grand experiment in the nature of information and reality, playing out over billions of years on a stage of stars and darkness. Our journey through this cosmic story leaves us not with an end, but with a new way of seeing. The universe is not a static museum of stars, but a living, breathing entity in a state of perpetual transformation. The brilliant spiral galaxies and the silent red giants are not different species, but the same entity caught at different moments in a single, breathtakingly slow narrative. From the violent ignition of the first stars to the final cooling of the last white dwarf, we are witnessing a grand cycle of creation and quietude that operates on a timescale our minds can barely grasp. We have traced how galaxies are strangled of their star-forming fuel, whether by their own supermassive black holes, the harsh winds of their environment, or the simple, slow exhaustion of their resources. We have peered into a future where stellar remnants, from black dwarfs to dormant black holes, become the sole inhabitants of these vast islands. This is not a story of destruction, but of profound change, a universe patiently writing its final chapters in fading light. This cosmic perspective reshapes our understanding of time itself, human history, the lifespan of our civilization, even the age of our planet, are mere instants against the eons-long fade of a single galaxy. We exist in a fleeting golden age of cosmic light, a temporary springtime in a universe that will spend most of its existence in a long, dark winter. That knowledge could feel overwhelming, yet within it lies a remarkable source of meaning. Our very ability to piece together this story, to use the light of ancient stars to decipher the fate of galaxies billions of years from now, is a testament to the curious spark of consciousness in the cosmos. We are the universe awakening to understand its own story. The silent galaxies above are not just distant lights, they are messengers from the future and archives of the past, reminding us of the beautiful, transient nature of all things. Let this exploration be a beginning, not an end. Look up at the night sky and see not just points of light, but entire narratives of birth, brilliance, and slow, dignified silence. Each faint, reddish smudge in a telescope holds an epic tale. We invite you to share your thoughts on this grand cosmic fate in the comments below. What does this vast timeline inspire in you? For more journeys into the heart of space and its deepest mysteries, subscribe and join us as we continue to explore. The next time you stand under a dark sky, remember you are witnessing a silent, majestic drama unfolding all around us, a story of light and time written across the